Let us spend a few minutes looking at problem number 15 of tutorial 3. This is a very important type of problem in that we learn to estimate the parameters of a model. It is very common for scientists and engineers to record laboratory or experimental data. That means we collect data on variables and then we try to relate those variables using a certain kind of a mathematical structure, which we call as a mathematical model. So a mathematical model will have variables and it will have parameters. So in this particular example, we have got two variables, d and t, and either through theory or because we feel that a certain kind of relationship might hold for this data, scientists have, let's say, proposed a model structure of this form. So this is the model that they have proposed. This model is called a power law model, or this relationship is called the power law relationship. Power law relationships are very common in engineering, particularly in chemical engineering, and in other fields like social networks, economics, biology, and fields like that. So here, D and T are the variables, and the scientists have proposed a model which contains two parameters, alpha and beta. So the job for us here is to find the best values, best in some sense that you define. You want to find the best values of parameters alpha and beta such that they relate D to T in a manner that is consistent with the data given. So if you look at D is equal to alpha t to the power of beta, that's a nonlinear model. And usually one resorts to what is called nonlinear regression when it comes to estimating parameters of nonlinear models. However, the power law relationship can be converted to a linear form, and that is what is illustrated here. D is equal to alpha t to the power of beta. So we are trying to find out alpha and beta. So what we are going to do is we are going to linearize this equation. That means in this case we will take the natural logarithm on both sides, let's say. So left side becomes ln of d. So if you take the ln of alpha t to the power of beta, you will get, using the properties of logarithms, right? That means log of xy is equal to log x plus log y. That is one identity. And then log of x to the power of n is equal to n log x. So using that kind of an idea, we are able to make the right hand side by taking the natural logarithm of alpha t to the power of beta. We can write it as ln alpha plus beta times ln t. Ln stands for natural logarithm. So what I'm going to do is I'm going to create a new variable. Instead of calling them d and t now, I'm just going to call this ln t as x. So this t data, right, whatever data we have, I'm going to take the natural logarithm of these numbers and call them as x. I'm going to take the natural logarithm of the numbers in d and I'm going to call that new variable, the logarithm of d, the natural logarithm of d, as y. Once I make those transformations for t and d and call ln d as y and ln t as x, I can call ln of alpha, because alpha is a number, logarithm of alpha is a number. So I can call that number as c. And I can just denote this beta, that parameter beta, I can relabel it as m. So what happens is, this model d is equal to alpha t to the power of beta can be transformed into y is equal to mx plus c. That means this is the equation of a line. What are the relationships between these two models, or the correspondences between the two models? Y is nothing but ln of d, x is nothing but ln of t, c is equal to ln of alpha, and m is equal to beta. We know it is easy to fit a line to the data sets. Typically, right, when you have data in high school, they teach us first of all to fit a line through it. That means to evaluate the slope and to evaluate the intercept c. The slope is m. You can evaluate the intercept and the slope quite easily using a graphical technique or through computations. So the point is, once we solve this easier problem in terms of the new variables y and x, you find m and c, we can just say, well, beta is nothing but m. And since c is equal to ln alpha, we can say alpha is equal to e to the power of c, exponential of c. We are done. So the stages are: first, create the new variables x and y, x from ln t and y from ln d. Then relate x and y through a linear model, through a first order polynomial if you like. Once you get m and c, you can recover beta and alpha, which is what we are seeking to find out using these relationships. Beta is nothing but m and alpha is e to the power of c. So this is how the code looks like. So first we input the data that's given to us, t and d. Then you can just visualize and see, right? So for example, I can plot t and d and see what is the trend it shows. So I encourage you to run this code, which has been already provided to you, and see what kind of a graph you get in figure 1. You will see that that graph has a curvature, which indicates the nonlinearity. So this is just for visualization purposes. It is not really needed as part of the problem solution that we have outlined, but it is always good to visualize data. Okay, so we see that. And then what we do is we do the things that we stated. X is equal to log of t. Log means natural log of t. Y is the natural logarithm of d. And then now what you do is you again visualize the data now, but you visualize it as x and y, not as t and d. So now you plot it and you will see that the transformed data, right, x and y fall on a straight line kind of a pattern. You will see that the curvature is gone. That means the power law relationship seems to be correct structure of relationship. But still we do not know what alpha and beta are. Therefore we are going to find m and c, and then we are going to use that to find out alpha and beta. In any case, the idea is very simple. So what we do is we use the polyfit command. Polynomial fit x variable, the independent variable x, which is nothing but ln of t now, but we'll just stick to x. And this is the dependent variable y. So this is the independent variable. This is the dependent variable. And this is the order of the polynomial we want to fit. We want to fit a first order polynomial, right? Because we are interested in fitting a line. So when you use polyfit, it gives you two outputs, P and S. S contains the statistical information that is not relevant to us for this particular problem because our scope is only to find out alpha and beta. So we are not going to make use of the statistical information that is in S. So if you look at P, right, P is like this, right? The equation will be P of 1 times X plus P2. That is what is contained in P. P will be two element vector now because we have asked for a line, right? A line has only two parameters. Therefore, the parameters P will have only two elements. The first element will be the slope or the coefficient of the highest power of your polynomial. Our polynomial is first order, so the leading term in the polynomial will be just x. So this P1 represents m, the slope of the line, and P2 represents the intercept or the constant term in the model C. So it is mx plus c. That is how you have to interpret P. If you use a second order polynomial, you will have P to have three elements. So P1 x squared plus P2x plus P3. That is what will be if we have fit a second order polynomial to it. If we did that, but we have not done that. But if we do a second order fit, P will have three elements, in which case the first element of P will be the coefficient of x squared. The second element of P will be the coefficient of x, and the third element of P would be the constant term or the coefficient of x to the power of 0. In any case, here we have fit only a first order polynomial. So what we have to recognize it is P in this case will have two elements. The first element will be the coefficient of x, and the second element of P will be the constant term. So P1 is m, and m is nothing but beta. So beta we can say straight away is p of 1. The first element of p is going to be beta because the first element of p is the coefficient of x, which is the slope, right? So m is equal to p of 1, therefore beta is equal to m is equal to p of 1. And we also know that c, the constant term or the intercept term in the model, is p of 2. And since ln alpha was c in the previous slide, so if you take the exponential operator on both sides, exponential of ln alpha will be equal to exponent of c, and exponent and ln are inverse functions. So it is like just left side will be alpha. So alpha is exponential of c and c is nothing but p of 2. When we do that, we get alpha is equal to 1 and beta is equal to 2 by 3. Therefore, we can say the experimental data tells us that d equals 1 times t to the power of 2 by 3, or just d is equal to t to the power of 2 by 3. This is a very simple problem without getting into the statistics, etc., on how you can find out the parameters of power law relationship models quite easily by doing the logarithmic transform of variables and using the polyfit command in MATLAB. Thank you.